everybody, I hope you guys are having a good day. So this video is about Hamiltonian paths and circuits. So take 3 deep breaths and let's make this math easy. All right, so we've spent some time on Euler circuits and Euler paths, and Hamiltonian paths are kind of similar because they're a special type of circuit and a special type of path. But the difference is that in Euler circuits, each edge is visited exactly once, and in Hamiltonian circuits, each vertex is visited exactly once. So in an Euler circuit, maybe I might start at vertex D and go through my entire graph and cover each edge exactly once, and that would be an example of an Euler circuit. But a Hamiltonian circuit is one where each vertex is visited exactly once. So this would be an example of a Hamiltonian circuit because I went to each vertex exactly once, and it doesn't really matter if you cover all the edges or not. Just like in Euler circuits, it doesn't matter if you visit the same vertex multiple times. Like in this one, I visited vertex A twice. And so with Euler circuits, the important thing is to visit each edge exactly once. And with Hamiltonian ones, you want to visit each vertex exactly once. And paths are very similar, but the difference is that your starting and ending point don't have to be in the same spot. So with an Euler path, you could cover each edge exactly once, but end up at vertex C, even though you started at vertex B. And with a Hamiltonian path, you're going to start at whatever vertex you want to start at, and you're going to visit each vertex exactly once. Even if you don't cover all the edges, that's fine, because Hamiltonian paths, you only have to visit each vertex exactly once. So now that you know what a Hamiltonian path and circuit are, why don't you guys take a look at this graph, pause the video, and figure out if there's a Hamiltonian circuit in the graph. All right, so on this one, it is not possible to do a Hamiltonian circuit because E is only attached to one other vertex. So like, let's say I chose E as my starting point. Well, I could go to C and then up to A, and then over to B, then up to D. But in order to get back to C, I would have to double visit vertex C. And so a Hamiltonian circuit is not possible because it's not possible to get back to where I started without double visiting a different vertex. However, it is possible to do a Hamiltonian path because if I start at E and go to C and then A and D and B, I've visited every vertex exactly once. And so that would be a Hamiltonian path. So when we're working with Hamiltonian paths and circuits, what we actually focus on more is optimizing them. So one of the things that's different about Hamiltonian paths and circuits versus Eulerian ones is there is no theorem or pattern to when a Hamiltonian path or circuit exists. So with Euler paths and circuits, we knew that if every vertex has an even degree, that a circuit is possible, and if only 2 of them have odd degrees, then a path is possible. So we had that Euler path and circuit theorem that allowed us to tell whether or not a Euler path or circuit existed in a graph. But with Hamiltonian paths and circuits, we don't have a theorem like that. There's actually not a consistent way like calculating the degree or things like that that you can use to determine whether one is possible. And so what we actually focus on with Hamiltonian paths and circuits is optimizing them, specifically in complete graphs. So these types of problems are often called the traveling salesman problem, because you think about, like, let's say there's a salesman who lives in Seattle and he needs to travel to like these different cities. If he wanted to find the cheapest way to make his sales trip and visit all the cities and get back to where he started, this is basically finding the cheapest Hamiltonian circuit, because you want to visit each one of the cities, which are all of the vertices, and end up back where you started, so that would make it a circuit. And so we're going to do a whole bunch of problems like this. And because there isn't a theorem that allows us to determine the existence of Hamiltonian paths and circuits, instead we're going to focus on optimizing them in complete graphs. Or in other words, we're going to find ways to determine what the cheapest Hamiltonian path or the cheapest Hamiltonian circuit is in graphs that always have a Hamiltonian path or circuit. Because complete graphs like this one here, where every vertex is adjacent to every other vertex, it will always be possible to visit all of the vertices and end up back where you started, because every single vertex is adjacent to all of the other ones. So what we're going to look at is what's the cheapest way. And these are often called traveling salesman problems, because the first time that people started talking about them was kind of in like a story problem where they said like, okay, well, like if a salesman lives in a certain city and he wants to visit all of these other cities and end up back home, what's the cheapest way to do that? And so we'll be talking more about those in future videos. But in your Hamiltonian paths and circuits assignment, you're going to have various graphs, and you're going to determine whether or not a Hamiltonian path or circuit is possible. And you kind of just have to do it by trial and error, because there is no theorem that determines whether or not it's possible. So if you have any questions, let me know, and I hope you guys have a good day.